Hi everyone. So this is going to be the last lecture for this course. After this, we're just going to do some more examples with dynamic analysis and things like that. So this is us kind of covering antivirus and anti-malware techniques. The things we're going to be covering are a couple of high-level approaches to basically how we scan for viruses. Then we're going to kind of go through the history of early scanning and detection mechanisms and looking at how they worked and how they sort of had to evolve over time to keep pace with malware. Then we're going to do a short exercise, and we're going to come back and look at what we call like second generation antiviral or anti-malware tools that took a more intelligent approach based on some of the malware evolutions that had happened. And then we're going to wrap up talking about ways that we can either clean up after malware and other things outside of just scanning that we can do to try to stop the spread of malware or at least control it. So the two sort of high-level approaches for initiating a scan for malware would be either on-demand or on-access. So with on-demand, this is the kind that you're probably used to the most, where you might right-click on a file in Windows and say scan with Windows Defender or scan with your AV suite, whatever it is. Or if you've ever configured regular anti-malware scans, to maybe run once a week, once a month, that we would consider on demand because the user is requesting a scan. The alternative approach is what we call on access, where a certain event inside the system causes a file or process in memory to be scanned by the AV scanner. So the idea is that the operating system's got some sort of trigger or process running in it that's looking for activities that will sort of cause the AV scan to happen. So you can write like file system hooks or syscall hooks. For example, maybe when a new file is being created on the file system, either by the user or via a download, or it's coming in off a USB stick, right? That's going to trigger some kind of system call to create a new file, and at that point the AV suite can hook that system call and trigger an AV scan. Right. So those would sort of be automated mechanisms for doing scanning. They're just different because the user's not necessarily or specifically requesting it. So early AV scanners, the way they worked, initially the first approach is what we would consider the most naive approach, right? The simplest mechanism to implement, which would be a simple string scan. And when we say a string here, we mean like a sequence of bytes, not like a plain text or ASCII string. So for example, a string in early AV scanners might have looked something like this. It's just a sequence of hex bytes that would hopefully be unique to that malware sample, right? So you could imagine maybe this would be an encoded string or something like that, or a series of instructions inside of a function that a piece of malware uses as part of its payload. The goal is to find a string that obviously wouldn't appear in regular or benign software, and that is hopefully unique to a specific malware sample, or maybe a family or a strain of samples or something like that. In the early days, apparently it was sufficient if you could find like 16 consecutive bytes, because programs were a lot slower then, or a lot smaller. So this was sufficient. And you may remember from your algorithms course the idea of substring searching, and that it can be a bit of an intense algorithm. You have stuff like Knuth-Morris-Pratt or the Boyer-Moore algorithm, which is kind of n squared, kind of not. It's like the runtime of a substring search is, worst case, you have the length of your substring that you're looking for is n, and the length of the text you got to search is m. So your worst case runtime could be m times n. But there's some slight improvements you can use. So it is kind of a slow thing to do substring searching. So what you're going to notice as we go through is that a lot of the improvements that were made to AV scanning routines were meant to really speed them up and look for efficiencies, because the inherent scanning algorithm is a little bit slow. Also, if the malware was written in a higher level language, like not straight assembly, so if it was written in C or something else, since compilers tend to have banks of sort of pre-formatted code that they write for standard operations, you're going to see a lot of replication across malicious code and benign software as well. So it becomes a little bit trickier. Maybe you need to make that string a little bit longer to search for, and every time you make the string longer, you make the scan a little bit longer as well. One of the first improvements that was made was wildcard scanning. So maybe we realize that within the string that we're searching for, maybe there's a little bit of variance in some of the bytes, either based on the malware family or the specific version, or it could even be that, these two first bytes here are from the malware, and then this can actually be part of the infected host, but we're not sure which 2 bytes it can be, and then another few bytes from the malware, a couple more bytes from the host, right? The idea of using something like a regular expression or a wildcard like these allows us to create somewhat more dynamic signatures, which will hopefully allow, for a more robust matching. Again, the efficiency here is still about the same, so it's still kind of slow, but maybe we can, at least match more samples or families or something like that. After wildcards, we have what we call generic detection. This is where we try to write some kind of a scan that might actually detect all known subvariants or all the samples within a particular family. The way you might come up with one of these signatures, if you do have a few different strains of malware from the same family, you can kind of diff them all together and look for common sequences of bytes. You then might go a little bit further and diff that against like some benign software to make sure that the sequence of bytes you found in that malware family aren't the same in regular software. Right, so that using a technique like that, you could maybe come up with a common pattern that would match a bunch of samples, right? Because there's times where you want to do sort of a generic match, and we'll see later there's also times where we want to do a more specific or unique identifying match on a particular sample. Okay. Another early technique was bookmarking. So maybe to help speed up our scanning a little bit, we know that our specific string that we're looking for, which is this one in red here, maybe it always starts at an offset that's like maybe 7 bytes from the start of the text segment or something like that. So rather than searching the entire text segment, which can be time consuming, we would save alongside the string in our, our anti-malware database, a bookmark byte or a bookmark location within the file. So when we start our scanning, we can basically jump right to that location and then search for the string and hopefully find it. If not, then maybe we can actually leave this file altogether, because we know that if it doesn't appear that's bookmarked, then it's never present. Worst case would be that it usually appears as a bookmark, but if we don't find it there, then we still have to scan the rest of the file. So there's the potential for speed up and optimization there. Another early technique was top and tail scanning. If you remember from our discussions on infection techniques, where malware would sort of either put itself at the beginning or the end of a text segment or something like that. So we're taking advantage of the fact that we kind of have an idea of where the malware is likely going to be inside the executable. So we can reduce the number of disk reads we do, the amount of space we need to scan. If we maybe only scan the first block, like, the first 512 bytes and the last 512 bytes of the text segment, looking for traces and looking for our signature string that we've generated. So that would speed up scanning a little bit as well. Again, there is the potential that you're missing stuff here, right? If like you're only scanning the text segment, maybe a new version of that malware has embedded itself in the data segment, so you might be missing that or something. But again, we're kind of going for speed improvements here, because at the time we're still in the era where hard drives were slow, CPUs were slow, so we were really trying to speed this up and catch most of the malware out there. A similar technique to a bookmarking is entry point and fixed point scanning. So rather than a particular offset within the file, we just kind of assume, well, a lot of malware likes to begin right where that entry point field that we looked at in the structure of the ELF and the PE. So in a PE, it was the address of entry point, and in an ELF file, it's E_entry. The malware will usually start at the byte that either of these two fields is pointing to. So when we open up a file for scanning, we jump right to that point, and we scan the first few bytes there. Fixed point scanning is similar. It's just that it may occur somewhere else in a different segment or something like that. You just can't always call it entry point scanning. Okay, so that's kind of the end of the first generation scanners. After this, we improve on them and they get a little bit better. But first, I kind of want you to do a little bit of an example so you can kind of internalize some of this. So if you hop over to Slate, there is an archive of a couple of sort of compressed sample programs. Don't worry, they don't do anything malicious. They just print strings, but they're all a little bit different. 2 of them are malicious because of the string they print, and one of them's not. So what you're going to do is write some Yara rules to do different kinds of matching on those samples. So the instructions on Slate should walk you through that. And once you're kind of comfortable with how simplistic string scanning works, come back and watch the second part of this lecture.